Hello, calculus. All right, this is notes lesson 1.8, rate of change and special limits. Okay, understand average rate of change and how smaller intervals lead to instantaneous rate of change. So we're getting really close to the end of this unit, and it's taking us right back to the beginning, which is kind of interesting. So the very first lesson we talked about was the tangent line problem and the area problem on the very first lesson 1.1. And we took intervals of the slope between 2 points. And as we got closer and closer and closer, we could get closer and closer to the slope at a single point. That is instantaneous rate of change. Rate of change is just another word for slope. Before we get there, quick review. These absolute value graphs, we have done these 100 times now. And there's lots and lots of ways to approach this problem. So first of all, maybe you'd want to look at it graphically. Okay, if you're allowed to use a graphic calculator, why not? I'm going to use my Casio, go to the graph menu, and we're going to type in -2 and then absolute value. That's under option, num, and then ABS. Absolute value of x minus 3 inside parentheses there, and then I need to divide by the entire x minus 3. And I really think the best way to think about this is we have x minus 3 over x minus 3, which reduces to 1. And the only difference being that numerator is always, that absolute value is always going to be positive. However, this one might change. So if we can go ahead and look at the graph. All right, hold on. Gotta go change my window here. Go back to a standard window. There we go. Oh, what a weird looking graph. Well, this is the Casio graph. It's not quite accurate. Obviously, there's no vertical line here connecting them, so that's kind of funny. But it is just these things. So what happens is we know x minus 3 over x minus 3 kind of sort of reduces to 1 because they're similar factors, right? But there's this -2 left behind. And so what's happening is at 3, it's undefined. And we know it's undefined at 3 because this common factor sort of creates like a hole at x equals 3. All right. And then beyond that, we know that for values, so for instance, if I wanted to just answer the limit to the left of 3, well, we can think about it kind of numerically. So maybe I want to think about this numerically. First of all, does the limit as x approaches 3 of the function exist? No, it does not exist. Remember, the limit from the left has to agree with the limit coming in from the right side. So it's clear that these don't agree. It's a mismatch. But we can still evaluate the left hand and the right hand limit. And maybe we want to think about it numerically. So 3 from the left means a number slightly smaller than 3. So that's going to be like, 2.99999. So let's see what happens if I were to sort of plug in 2.999. Okay, so here in the numerator, we get this number that happens to be a negative result, but because it's an absolute value, it's going to come out as positive. We're left with a -2. Whatever this is, it's a positive result. All right. Down here, 2.999 minus 3 is going to be a negative result. All right. So when we are slightly to the left of 3, we get a negative divided by a negative, which turns into a +2. And so that's how our y value is 2 on the left side of 3. Okay, we can do a similar thing here if we want to be just to the right side of 3. So that'd be a number like 3.0001 maybe. So -2, and then if it was 3.001, 0001, I guess, over 3.0001. Well, again, there's a -2, and then 3.001 minus 3 is some positive value. I don't really care what the number is, but it is a positive result because it's inside the absolute value. So that has to be positive there. But this part also would be positive, a positive result. And again, they're going to reduce anyway. They're the same factor. And so we're left with that -2 value. And so that's why you can see over here to the left of 3, our output is in negative territory, -2. Okay. These limits, the limit from the left does not equal the limit from the right. Therefore, the limit at 3 does not exist. Rate of change, what once was slope. So we're going to hear rate of change a lot, and we're going to hear average rate of change, or AROC, and we're going to hear instantaneous rate of change, or IROC. I know, IROC. All right, funny joke. Okay, so average rate of change is the slope between 2 points. We know that. It's the same as slope. It is the change in y over the change in x. We've talked a little bit about that notation before, or simply it's y2 minus y1 over x2 minus x1. We know this. Average rate of change is just fancy for slope. It can also be the slope between 2 points in time. So we might have, it could also be the change in some y values over the change in time, which would be y2 minus y1 over t2 minus t1. So we could be talking about time. And what's really important here is that there's probably units. And so this might be like miles per hour or feet per second. But that is, when I think rate of change, I'm usually thinking, what are the units? And if you pay attention to units, that like speed and velocity, these are all units that are very, very handy. And for us in calculus, they make a big difference, and they can help you answer a question just looking at the units. I did that so many times. Looking at the units told me, did I need to take a derivative, or do I need to integrate? And we'll talk more about that later. Instantaneous rate of change is the slope at a single point. It's the slope at 1 second, or the slope at x equals 5, okay? It is also the tangent, okay? So it is the slope of the tangent line. And we'll talk more about that soon. At a single instant in time, it can be approximated though. So we can approximate it, and that's what we started doing. We're approximating the slope over smaller and smaller intervals. So that's what we're going to be figuring out in the next unit here, which is cool. And so here we go. Let's try a couple. Example 2. Given f of x equals x cubed minus 2x squared minus 10. I'm going to go ahead and plug that equation in just because I'm lazy. And if I have the opportunity to use my calculator, I'm going to do it because it makes my life easier. So I'm just going to look a little sketch of that. And the first question says we want to find the average rate of change, so AROC, between x equals 2 and x equals 3. So what we need to do in order to do that is we need to find those ordered pairs. So I shouldn't have written that down. The first thing we want to do is figure out what is our function value when x is 2, and what is our function value when x is 3. And that's why I plugged it into my calculator, because then I can just do trace 2, and the output is, oh my God, I can't read it. Well, that's annoying. Oh, trace 2. Oh, how useless was that? That's really frustrating. Man, you mean I got to do it by hand? Ugh. 2 cubed minus 2 times 2 squared minus 10. All right, that's 8. Minus 8, well, okay, is 0, is negative 10. Okay, okay, maybe that's negative 10. I'm going to trace 3, and I get negative 1. Okay. So, of course, you could just plug it in if you needed to. But there we go. We have an x value and a y value. Function notation is very, very useful. If we want to find AROC, I need to see the slope formula that you're doing. So that would be f3 minus f of 2 over 3 minus 2. That is the slope formula. We get this ordered pair 2, -10 and 3, -1. So what did I just do? I took y2 minus y1 over x2 minus x1. And that's what I did. This is called the difference quotient. Yeah, it's just slope. How about that? Difference quotient. Difference because we're subtracting some things, and quotient because it is a giant quotient. How about that name, huh? Difference quotient. This is an AP essential item that they mention like on every page in the AP book. Make sure your students use the difference quotient. If you wrote -1 minus or plus 10 minus a -10 over 3 minus 2, that counts. But I would like to see this. And I'd rather see this than an answer. Let's see, we get 9 over 1, so just 9. And in fact, on the AP test, you could leave it just like this. That's fine answer. It's perfect. It's not incorrect. If you added wrong, you got 11, you'd get it wrong. If you left it like this, you'd get full credit. All right. Find the average rate of change between x equals 3 and x equals 4. Well, again, we want to find out what is happening when x is 3 and what is happening when x is 4. So I'm going to use my handy-dandy calculator. When x is, oh, we know it was 3. It was -1. And when x is 4, we get 22. And so we want to, again, find the average rate of change. So that is going to be y2 minus y1 over x2 minus x1. All right, remember, so these are just ordered pairs, and it's you know, well, technically it would be 22 minus a -1 over 1. So we get 23. Okay. What is that talking about? Well, on our curve, which I'm going to change my window, maybe make it a little lower, -50. Oops. All right. There we go. So I have this curve, right? And this is way down at -50 and up to 10. Okay. So it's always good if you're going to draw a picture to label what your axes values are so you can tell. Well, we took the slope between x equals 2 and 3. And that was, let's pretend this was 2 and this was 3. So here was 3 at -1 and 2 was at -10. So this was the slope between these 2 points. And then between 3 and 4, which was way up here at 22, we had this slope between these 2 points, like this. All right, so we had that green line slope and we have the red line slope. And so then the follow-up question is, which of these is likely to be the better estimate of the instantaneous rate of change at x equals 2.4? Well, 2.4 is about right here, which falls in between 2 and 3. So what is better? Is it better to be in an interval between 3 and 4, or do you think it's better to be in the interval that actually contains your value? Yeah, so definitely, so 9 is the better estimate. For rock at 2.4, at x equals 2.4, because it is in the interval from 2 to 3. All right, it makes sense that if you want an instantaneous rate of change and we're trying to approximate that interval, that at least that x value should be within the interval. Now, the closer we can get to 2.4, the better that approximation is going to be. If I had the value at 2.3 and the value at 2.5, that would be a pretty good estimate of the slope at 2.4. Okay, so the closer you can get to 2.4, the better your answer. All right, example 3. Again, you might need to pause and write this stuff down. The data in the table shows the mileage from the start of a 4-hour car trip recorded at 1-hour intervals. Assume the car continued in the same straight line. This is the drive from about Casa Grande on I-8 to San Diego, that straight road that just goes forever, and it just doesn't, this is that drive. Okay, and so we have the time in hours from when we started at 0, and then this is the first hour, and the second hour, and the third hour, and the fourth hour of our drive. And this is the miles from starting. And I did this M of T and T, so I wanted some notation there. All right, find the average rate of change. And we gave you a hint, hey, it's average speed. Well, when you think about speed, that's usually like miles per hour. All right, that is a big, big clue. And you want to pay attention to units, so get used to looking for units. They're really helpful. What is the average rate of change of the car for the final 2 hours of the trip? So that would be this third hour and this fourth hour. So the final 2 hours of the trip, starting at 2 and ending at 4, we want to find the average rate of change. And so if you wanted to write using fancy notation, that would be M at 4 minus M of 2 over 4 minus 2. That would be the best notation to use. And that is, again, the difference quotient. Well, what's the miles after 4 hours? Well, that was 250 miles. And the miles after 2 hours was 120 miles. 4 minus 2 is 2. And I need a calculator. I need to go to my menu. Okay. 250 minus 120. I can't do math right now because divided by 2 is 65. All right, so one thing we want to talk about is miles, or not miles, units. This was 250 miles minus 120 miles, and this was 4 hours minus 2 hours. So we get units, and they do often give you points for units. Like it's a whole point on the free response sometimes. When they say, calculate the speed of the car, then you'd get 1 point for your answer of 65 and also a point for the miles per hour. So it's really important to keep those units on there if you're given units. Just units. Estimate the instantaneous speed at the 1.5 hour instant. Well, 1.5 is between the first and second number here. And so that is the closest we can get to 1.5. I don't have data at 1.5, but I can go around it. So the approximate instantaneous rate of change is approximately, you'll notice I'm using approximately, M of 2 minus M of 1 over 2 minus 1. I like doing this because you recognize the pattern, like you're getting pattern, right? Okay, so this is our function after the 2 hour mark is 120 miles minus 55 miles over 2 minus 1, which is 1, all right? Oh, 120 minus 55 is 65. Again, miles per hour. Per 1 hour, per hour, doesn't matter. So that is approximately 65 miles per hour. Pretty good. All right, and then during which hour does the data suggest the car reached the greatest instantaneous speed? So first of all, this word suggest. I don't know what happened during this car ride. I don't know if they maintained a constant speed, or maybe they went like super duper fast at the beginning of this hour. They're going like 85. And then at like 45 minutes, the cops started following them. And so they slowed down to like 35. We don't know what happened 45 minutes in. You know what I mean? Lots of things could have happened. We only have this data. So we use the word suggest because we don't know really what happens in between just these data points. And so what we want to do then is basically look for what is our average speed here in this first hour. Well, that's a change of 55 in 1 hour. So that little interval is 55 miles per hour. From this first and second hour, we already found that one. That was 65 miles per hour. 2 and 3, well, that's a difference of 60. So that's 60 miles per hour. And then here, let's see, I don't know what 250 minus 180. That's 70 in 1 hour. So that's 70 miles per hour. All right, so I'm just roughly calculating that speed, average rate of change every hour. So the difference is 70 per hour. All right, so it looks like this is in the fourth hour. This is your first hour. This is the second hour. This is the third hour. And from 3 to 4 is the fourth hour. In the fourth hour, the greatest speed is 70 miles per hour. Okay. So again, just calculating average rate of change a bunch. And the closer we can get to a point is instantaneous. All right, that's not so hard. So here we have limit of a composition. This is tricky. And I have some very tricky problems. And in fact, I have a worksheet that you'll get next semester when we start studying for the AP test called the tricky limits. And it's challenging. So it took me forever to figure out how to teach this, but I think I've got the easiest way I can figure it out. Easiest way I can figure to do it. So a composition is when we have like an outside function and an inside function. And we've seen things like this before. But here we have this limit notation. F and G are functions, and we want to find the limit of the composition. So we have this outside function F, and we have the inside function G. And so I'm just going to call this G of X function the inside piece. And so if we want to figure this out, it's a big complex process, but I think this is the best way to do it. What we have to do, order of operations says we have to figure out everything inside first. And so that's what we're going to do. We're going to start by finding the limit as x approaches c of the inside function. And that's what this is. The first thing we need to do, so as you see the big parentheses here, find the limit as x approaches c of the inside function. Inside function, okay? And then once you figure out that answer, then this is going to clean up really nice. That's going to change whatever this value is. I don't know what the value should be. It's no longer c, it's something different now. So then we can evaluate the limit as x approaches this new result of the outside function, okay? So this is where we're going to start. So here's a little example. We want to find the limit as x approaches 3 of f of g of x. So to get started, I need to find the limit as x approaches something of our outside piece, okay? We have to start with the inner function, and we get to start with this limit here. The limit as x approaches 3 of g of x. So that's what we're going to do first. Let's figure this out. What is the limit as x approaches 3 of g of x? Well, here's my g of x function. It's a lovely parabola, nice and smooth and continuous, which means I can do direct substitution. So I'm going to go ahead and plug in my 3. That's going to be 9 times 2 is 18, minus 10 is 8. So this is the limit as x approaches 3 of g of x is 8. And so we get to now figure out Now we can answer the question. As x approaches 8 of the outside function, what's our result? So see how that sort of changes things? We get this new value that we have to approach. And now we're referencing our f of x function. So now f of x is a cube root function. If you remember, that's a breaking wave function. All right, this one was a nice smooth parabola. This one's nice and smooth and continuous too, so I think we can do some direct substitution. So that's just going to be the cubed root of 8, which is 2. Okay. All right. So once again, down here, we got some new f and g functions, and I want to find the limit as x approaches 1 of g of f of x. So again, we need to start with the inside function. So I'm going to have my limit as x approaches something of the outside function. And I need to start on the inside using what they gave me. Limit as x approaches 1 of this inside piece. So that's where we're starting. Right here, we want to figure out the limit of the inside. Well, when I look at this inside function, it's a nice smooth parabola. It's facing down, so it's continuous. So I know I can just plug it in directly. And so that's going to be 4 minus 1, which is just 3. So I'm going to redraw my limit now to clean it up. So now I have the limit as x approaches 3 of g of x, of my outside piece. G of x, again, is a square root swoop. And so it's continuous. Yeah, continuous on this interval, so that's good. We can plug in 3 then. So that's going to be the square root of 3 plus 1. Square root of 4 is 2. Man, every time I get the same values. I do not plan that. It just happens. All right, we're going to try some more with these using generic functions. So here we go. Again, you might want to pause and copy down the graphs. These are very interesting. So first of all, we want to recognize what is a composition and what is not. So these up here are not compositions. These are simply limit properties. So here we have the limit of something being squared. So that is simply going to be the limit as x approaches 3 of f of x. And then we just get to square that result. In the denominator, we have the sum of 2 functions. So that's the sum property. It just says I get the limit as x approaches 3 of g of x plus the limit as x approaches 3 of a constant function. All right, so these are just using the limit properties, nothing too tricky about that. Let's see what happens. The limit as x approaches 3 of f of x. Here's my f of x graph. As x approaches 3, our function approaches the value of 2. So that's just 2 squared. And let's see, the limit as x approaches 3 of g of x. Well, here's 3. And as we approach from the left and the right, we're approaching the value of 2. And then here we have the limit of a constant is just the constant. So this is 4 over 3, it looks like. Okay. And that one's done. This one is a composition. So this one is going to be our sort of limit of the inside and then evaluate the limit of the outside. So I'm going to rewrite this. So that's going to be the limit of something as x approaches something. We have to first do the limit as x approaches 2.5 of our inner function. And then we get to worry about the outer piece. So first, I'm going to start here in red. I want to find the limit as x approaches 2.5. So here's about 2.5. And again, we can see that our function is approaching 2. So this whole thing is 2. So I'm going to go ahead and rewrite that. Limit as x approaches 2 was what we found first. So that was the limit of the inside function. And now I want to find the limit as x approaches 2 of our g of x function. So now here's our 2, and the limit as we approach this function looks to be about 1. Okay. And then last one, again, we have another inside-outside function, composition. So I'm going to start with rewriting this. First, I need to look at my limit of the inside function. Limit as x approaches 3 of g of x. That's where I'm going to start, and then I'll worry about my outer function. All right, so my limit as x approaches 3 of g of x. This is really tricky. When I look at this limit, it's very tricky because remember, limits have to come from the left and the right. So as I'm approaching from the left side of 3, I am approaching the value of 2 from below. And as I approach 3 on the right side, I'm also approaching it from below. So, which is very interesting. I'm not approaching it from below and above, getting both sides of things. And that's really an important distinction. This is approaching 2 from below. Why do I care about it? And I didn't care about it here. Or not, it wasn't here. It was here. Yeah, didn't care about it here because this wasn't inside of a composition. So here I have to take another limit. And so this is really important that we recognize that because I have to take another limit, I have to recognize that I'm only coming from one direction. I'm only coming from underneath the value, slightly below. And so now I'm going to find the limit as x approaches 2 from below that outer function f of x. And why does that matter? Well, if we were approaching from below and above f of x, then this limit doesn't exist. But because we're only approaching from underneath smaller values of 2, well, all the small values of 2 are here, which does exist. So it's kind of a tricky distinction, but we're approaching 2 from values that are less than 2, which means we're approaching 1 for this particular limit. If it was just 2, meaning it approached from values lower than 2 and values above 2, then we'd have to come in from both sides. That limit does not exist. Okay, but here we were just approaching from one direction, so from one side does exist. So very interesting, very tricky. And again, we'll talk more about this. So you've got a couple of these to try out today in your homework. All right, ladies and gentlemen, good luck with that. Have a great day.